on the test. I'm not going to give you anything that I haven't already given you, I think, either earlier today or that I'm not going to review right now. Although there might be one that's a little different, but that's just, I reserve the possibility of one mystery problem. And it won't be worth a huge amount, it's going to be worth on par with the other problems. So I won't be able to, one mystery that's worth 40 points, it won't be like that. Okay, so the first question I wanted to have has to do with resultant forces. So as an example of that type of question, that's what I'll do, I'll give an example question like that. So given, say a force, we'll call it force 1, and we'll say it's 3 and 8, and force 2 is equal to, let's say 10 at 120 degrees. We'll say find F3, and these are vectors, is equal to F1 plus F2. Maybe, I'm not going to ask all of these things necessarily, but show graphically how you get that. Maybe, and maybe you want F3 in polar and XY form. And then what is the acceleration vector? And it's going to be in the same direction as the force that leads to it. But this is a question that really it's just a matter of, does anybody have a question about how you might go about solving this question?
Find the XY of F2.
At each one, yeah, and just add those, right. And really, it's going to be a pretty straightforward question. I might ask you to show it graphically how it looks on the axis or something. But and then remember, like if it's in the third quadrant, use what we talked about before, how to get the angle with respect to the positive x-axis. And the main thing here is to remember the this acceleration vector. You'll have F3 is equal to mass times A3. I should call that A3 really. And so you can find the acceleration vector very easily that way by realizing that it's this resultant force that leads to that. A related question that I had down initially as a separate question, but really it's all part of the same question, the same cluster of ideas, is that what force will take F3 into equilibrium? And remember, this equilibrium, what it means is that if you add all the forces that are acting on it, it goes to 0. So that would mean that F1 plus F2 plus the force to go to equilibrium will go to 0. And that's just saying F3 right there, the same thing as saying that. So what makes this go to 0? What this means is that Fx would be 0 and Fy would be 0. Its magnitude would be 0 and its angle is going to be 0 if it's in equilibrium. So what force will take that into 0? And in fact, as you saw in the force table, something of this nature, say for instance, if you had force A, and let's say it was equal to 10 newtons at this angle, well, going directly opposite force B at 10 newtons, this would result in equilibrium. So it's just a question of having the same magnitude, but the opposite direction with respect, and you have to give that with respect to the positive x-axis, if you have that. So if this angle were, let's say it looks like about, 150 degrees, this angle here would be 150 degrees plus 180 degrees. To make it go the direct opposite way and still be with respect to the positive x-axis. So find the resultant force, and then maybe I might ask, okay, what force, I could ask, okay, F1 plus F2, find the force that brings them into equilibrium. So then you can find F3 and then just increase its direction by 180 degrees, and that would give you the force that takes it into equilibrium. And so that's one of the questions. I had that written down as two questions, but really, I can make that into one question, maybe with a couple of parts or something, yeah.
How do you find acceleration without a mass?
I'm gonna have to give you a mass. That's a good question, and I will give you a mass. Without a mass, you don't, really. Okay, other questions? I think probably most people feel fairly comfortable with this question right here, it seems like. Or is that not the case?
Are you gonna work it out?
Oh,
Yeah, we were waiting for you to look at it.
oh, okay, if you wanted to work, okay, yeah. Okay, that's easy enough to do. Okay, so, I want to make sure we have enough time to get to all the questions. We'll work out as many as we can, and if we're running low on time at the end, I'll just give the question, and it refers back to things in your notes, and I'll sketch out a solution, but we'll work out as many as we can at the end. Okay, so what you can say here is that, you know that F3x is equal to F1x plus F2x, and then F3y is equal to F1y plus F2y. And we already have the x component. This is the x here, and this is the y component here. Since this is F1x and this is F1y. For F2, we have to be a little bit more careful about that. And I'm going to go through these a little bit faster because it's a review. I'm still going to put everything up here, but I might not put all the numbers up here. And it's all four. This will be F2, X will end up being 10 sine of 120 as we're accustomed to breaking down the x and y components. F2y will be 10, I'm sorry, I got those reversed. It's harder to show on the triangle with 120 degrees because it just doesn't make a whole lot of sense. If you draw something that looks like this and say, okay, this is the fx and this is the fy, but that's the degree out over here, it's nowhere in the triangle, so it always seems bizarre to me that it still works with sine and cosine. And you can see that if this is fx here, then this would be cosine, and this would be sine over here for it. But that's the way it works out. What I might do is give you one in the first quadrant to avoid an angle like that, because it seems really weird to me that it works that way. It does work that way, but it just seems weird. I haven't seen work something out with it to make me feel satisfied with that, although I know it's true. Okay, so once we have that, then we can say, okay, we can find out what quadrant it's in. We can get the magnitude of F3. Again, it's just the positive square root of F3x squared plus F3y squared. And the angle, well, that depends on the quadrant. And we talked about, and it's in the notes, what to do if it's in the first quadrant, the second quadrant. And to find out what quadrant it is, you can plot it out with the F3x and F3y, and that's the first, second, third, and fourth quadrants, and all that's also in the notes. I know this is not completely all the numbers here, but this probably is, well, if you want to show it graphically, you would just, I'm not sure if this is where it's going to be, you do F3x, if it was negative, F3y, and then connect it from the, I don't know if it's in this quadrant, we haven't worked out the numbers, but I think in the interest of time and getting to the other problems, I think most of you can maybe see where it goes from here. Is that, am I right in thinking that? Okay. And you also have examples in the notes that will kind of prompt you to go the rest of the way. Okay, again, because we have 8 problems, I wanna make sure we get to all of them.
What would the formula be for the acceleration of 3?
Oh, acceleration, okay, that's the net force. So for the acceleration of 3, what you have is something like this. F3 is equal to the mass times A3, and I'm gonna give you that mass.
Okay.
And so really all it's gonna be is that the vector's gonna look like this. It's gonna be the magnitude of 3 divided by the mass, and it's gonna be the same angle as F3, because it's gonna be in the same direction as the force that led to that acceleration. So it's gonna have that form, so once you found the angle stays the same for the acceleration, but it just is the magnitude of the force reduced by whatever mass I give you.
Thank you.
Sure. Okay, other questions? The next question, I think it's one that we almost did last time, but didn't quite get to it. It's gonna be, something you may find a really straightforward calculation. But what I'll do, I'll call this problem 2, we're only gonna have 7 because 1 and 2 are combined into one problem here. So let's say we're given an initial velocity vector, let's say of 100, and we'll do 30 degrees. How high will it go? And again, we're going to assume no friction with the air. Or another possibility is the initial velocity is 0, and it starts at maybe 100 meters. What is its final velocity? And these are 2 questions that we can answer. They're like the same problem, but in reverse. For the first one, the idea is that at the beginning, it's all kinetic energy. At the end, it's all potential energy. Since we're starting at the ground level, there's no potential energy at the beginning. I'm not writing that out all the way here, but at the end, it comes to a stop before it turns back around, and so it's all potential. So what you have is mv initial squared over 2 is equal to mgh. But this is vy initial, because it's only the component that's going straight up. The x component doesn't make any difference for it. And so we can cancel the m's, and we get, we're looking for how high it goes. So we get vi squared over 2 is equal to gh. So we have h is equal to vi squared over 2g. But now we need to get this. Using our velocity vector, we only want the vi in the y direction. That's the only thing that's moving it upward, and that's the only part that counts is its kinetic energy in the y, from its y direction component. And again, we have this here, and so we have the sine of 30 degrees is VIY over 10. So we have 10 sine of 30 degrees, which is 5. Oh, so it says 100, okay, right, thanks. Okay, so we have 50. 50 is our initial velocity in the y direction. And then we can use that over here. I'm sorry, this is getting to be a little bit out of sequence over here. And then I'll try to keep it like this. So we're going to put this into the formula. So we have h is equal to that 50 that we just solved for, square it over 2 when we're using the fiction that gravity is 10. So we get 2,500 over 20, or about 125 meters is how high it goes. change the other one and do it in reverse to show how it works. We'll make the other one start at 125, and we should get the same 50 out of it. Okay, so questions about this first part here. You have an example, I think like this, we did one similar to it in the notes before. Sorry, that kind of got bunched up right here. Get some of these chairs out of the way. I hate the little bit of space they give us. I think it's, well, that kind of limits the viewing here too. Okay, so let's look at the second way to ask it. If I instead ask, given VI is equal to 0, and it's 125 meters tall, what is its final velocity in the downward direction? And that's downward. We have at least two ways of getting this. Well, we have at least three ways of getting it. We can say the potential energy initial is equal to mv final squared is equal to the kinetic energy final. That's one way of getting it, and we'll kind of do 2 or 3 ways here to show that we can do it that way. So this is one method. The second method would be df squared is equal to vi squared plus 2ay. That's a second method. Then there's a third method too, but we'll kind of follow these two down here. Okay, so here we have mg h initial is equal to mv final squared over 2. Luckily, the m's cancel out, and we get 2ghi is equal to vf squared. So we have 2 times 10 times 125 is equal to v final squared, and that's what, that's again 2,500. Positive square root of that, if you count it as a downward direction, is equal to vf, or again, it's equal to 50. We get the same number out of it again. Likewise here, this is what we want v final squared. And we have an initial velocity of 0, 2 times 10, and it goes down 125. We're counting downward as positive here, so we get vf squared is equal to, again, 2,500, or vf is equal to the positive square root of 2,500, and that's equal to 50. That's a second method. Then there's a third method that we could also use for it. Any one of these is perfectly acceptable. It's whichever one you feel best with. You can say, okay, y is equal to 0. We could have at times 0 here at the top. You can have this be the positive y direction. This is 125 meters. This was a lot more complicated. We can do it, but it's not the best use of our time now, so these two are the most direct and easy ways to get it.
So overall, you're looking for how high it goes up and down?
Well, yeah, I'm either going to ask for, given an initial velocity vector, how high does it go? Or given an initial height where it has no downward velocity at the start, what is its final downward velocity going to be?
For this problem, we had to look for both the top and bottom.
Right. And what Charles is looking at is that in one case, the kinetic energy goes to potential. The other, the potential goes back to kinetic energy. And so what you're looking for is its component of velocity in the y direction to begin with, and that will give you how high it goes. The other one, you're looking for just the downward component of its velocity, and you can get that from that same relationship, that potential turns to kinetic, or kinetic turns to potential. Okay, other questions about this one? I know this is going maybe a little bit faster than you all want to see it, but a lot of this, most of this is in the notes, and I just want to be able to show you, and you know what the problems will be now. You can focus on that with the notes. I don't know, is there a tutor available on Fridays?
Yes, 8 to 5.
8 to 5, okay, yeah, so you have a lot of chance to ask questions too. Right, when I heard some knocking, I don't think I'm hearing things that maybe, but probably not. Okay, so next question let's look at. Oh, this one, okay, okay, given if, okay, so the third kind of question that might be on the exam, we'll have a flat surface, I'll give you a mass, and for this one, I'll just make it 2 kilograms. It's such an easy mass to work with, and, okay, yeah, and we have this, and let's say we have an applied force of 10 newtons, and let's say we apply it for 3 seconds. We're gonna say there's no friction involved here. So we have no friction, an applied force of 10 newtons in that direction for 3 seconds only, and so in 3 seconds, we're gonna say, okay, what is the acceleration vector? That's one question, and that's gonna be really easy to get because it's going at 0 degrees with respect to the positive x-axis. How far does it go in 3 seconds? Then we're gonna ask for the kinetic energy final and the final velocity. Then we'll also ask for the energy from the applied force and the power. So those are just going to be small calculations once we get going with this thing. Okay, so the first question, A, we just want to know what the acceleration is, and so we know that the force applied is equal to the mass times the acceleration. No other forces are involved. So we just have 10 is equal to 2a, so 5 meters per second squared is a. It's in the positive x direction, and so the acceleration vector in polar form is 5 at 0 degrees with respect to the positive x-axis. And what I ask, in this case, it will be 0 degrees, it's not going to be on a slope, it's going to be 0 degrees with respect to the positive x-axis. Or if I wanted to give it, if you wanted to give it in polar form, I mean xy form, A with no component in the y direction, it's all in the x direction. So this is polar, and that's xy form. Okay, how far does it go in 3 seconds? I'm going to tell you the initial velocity. It's either 0 or it's, we'll make it 0. That's going to make it easier. That's 0 at t is equal to 0. And then we can say, okay, how far in 3 seconds? Well, this was part A. So part B, how far in 3 seconds? We need this position equation. Since we don't know its final velocity, we can't use the other one. And to find the distance, it's going to be easy enough to let the initial position will be 0. This is 0. And again, we just have 3. And it's really the same case we did before. 3/2 t squared. So that means.
Yeah, it should be 5.
Seconds. Oh, no, it is 5. You're right. Okay. So it's not the same case as before. Okay, so 5 meters per second squared. So we have 5/2 t squared. So we have x at time 3 is equal to 5/2 3 squared. So we have 45 over 2. 22.5 meters this thing has moved. Okay, so that's how far it's gone. Now we're going to need to get the final kinetic energy, its final velocity, which is better to get, well, you know what, we can get it in 2 different ways, and we'll show both of those. The final kinetic energy. Well, we know that all the energy, so C, KEF, is going to equal the energy applied, since all of it was used to accelerate the object. We didn't have to work on friction, there was none of that going on there, so we can say energies have applied, that's force applied times the distance. We said the applied force is 10, the distance is 22.5, So we have 225 joules is the kinetic energy final. The final velocity, we're gonna double check that we're gonna get it in two different ways. Okay. But let's kind of box that in. And so VF, what is that equal to? Well, we know that M V final squared over 2 is 225. It started off with no kinetic energy, so all of what it gained is from that final velocity. Well, again, we have the nice thing that 2 is the mass. So we're gonna have VF squared, it's gonna be equal to 15. It's gonna be the positive square root of 225, and that's gonna be 15 meters per second. We could calculate it another way. Method 2, we know that VT is equal to V0 plus AT, which is 0 plus 5T. So V at time 3 is equal to 5 times 3. And again, we confirmed that it's 15 meters per second. It's a good way to double check it if you can remember how to do that. Kind of double check to make sure you're on the right track.
So I guess we don't use a DF square equals V.
We could, yeah, we could. Well, let's see how that would work out. Okay, so let's look at a third method. So method 3, we could say VF squared is equal to V initial squared plus 2 AX in this case. So this is 0, 2 times 5, and we said the distance was 22.5. So we have VF squared, and that evaluates out to 225. And so again, we're getting the same thing. It's the positive square root of that. And so this is nice. You can see how all this works together. We look at 3 different ways of getting it, and our answer's been confirmed with each one of these. If it wasn't confirmed, we'd have to either suspect that the equations were not right, that they've been shown through a lot of experience over hundreds of years to be correct, or that we made an algebraic mistake or misremembered the equation or written it down wrong. Okay, so, wow, and we've already calculated the energy applied because we said that was equal to the kinetic energy. That's where it went to give it kinetic energy. So we've already done that one. And again, it's just FA times D, so that's 225. And then finally, power was energy over the time taken to deliver it. So it was 225 joules was delivered in 5 seconds. So we end up with 45 joules per second, or watts. And that's that problem. And I think almost certainly, I mean, you won't know exactly which ones are going to be on the test, but this one will be on the test. I'll tell you, this one's going to for sure be on the test.
Why did you divide it by 3 if the time is 3, or 5 if the time is 3?
Because I forgot that. I made a mistake, thank you. It's divided by 3, and so what that's going to be 75. So 75 joules instead, joules per second, or watts, thank you. Okay, so,
Why is it over 5, not 3?
oh, because 3 was how long it took to deliver that energy, and I mistakenly thought it was 5 and put the wrong number there.
Oh, so it is 3?
Right, because I go, how far does it go in 3 seconds? And it's and the force is applied for 3 seconds. That's when it's giving the energy. Over the 3 seconds, that force that gives the energy is applied.
So is final kinetic energy and energy the same thing?
Or yeah, they are in this case. We could have calculated this a different way. We could have calculated the final velocity first, and then did mv squared over 2. We would have gotten the same answer. But we also know that all the energy, in this case, none's being worked against friction, so we know all of it's going to accelerate the object, that is to give it kinetic energy. And because we know that, we can equate the two. Because there's nowhere else the energy is going in this case. Since there's no friction to overcome, we're not going uphill against gravity. And we haven't mentioned any kind of electrostatic repulsion or anything like that, or any springs coming up against. We'll get to springs later on. Okay, other questions? Okay, we've got a few more questions to go here. really all I'm looking at is, I have four more questions now, and I combined some of those, so we're doing pretty good on time here. I want to get to these first, and if you have questions about homeworks, you can ask those. And I want to say that, if I give time to ask the questions, what we could do with the test is that we could have it during the second half of the class period on Monday. That would give you a chance to come to class, ask any questions you get over the weekend, and then we'll cover some new material before the test, because I don't want to break up having one classroom move into the next classroom. Who would rather have the test first thing on the first class we get there and have no chance to ask questions on Monday? On Tuesday? Not nobody, I guess. That makes sense. What we'll do is that we'll start with the new material just to get that out of the way, and then so you can turn your complete focus to the test after maybe half an hour of new material or something. Because I don't know how many questions there will be for the test. Or we could kind of have the questions first in case there are a lot of questions that will take up the entire time. I want to make sure they were all gotten to be asked. We'll do that, and then in the leftover time, we might do a little bit of new material, and then you can turn your focus back to the test. Okay, so let's look at the last 1, 2, 3. Well, I've already given that one. Okay, no. Okay, so I have 4 more to give you here. I'll do this one next. It's one that's a nice question here. And it's also going to be a very quick calculation here too. This last one here, or this next one. This is question, I guess, 4 that I've been giving you. And we'll have an object on a slope. I'll give you, we'll say it's 40 degrees this time. That looks about right. Let's say it's an object that has, we'll keep the usual mass of, we'll give it a mass of, again, 2 kilograms. That works as well as any other. And we'll give it a mu sub s, a coefficient of static friction. We'll give it a very low one, 0.1. And so we're going to ask the question with this, does the object slip? That's going to be the question. Does this object slip? It has an initial velocity of 0. It's just, you set it down there and see if it slides down, does it slip or slide down this incline? And the key question to asking this is to look at what forces are acting on it. You look at down the slope, we have Fg x prime. Opposing it is the force of static friction, and it goes from 0 to Fs max. And kind of taking them out of the slope and kind of just drawing them, but realizing they're on a slope, it's going to move only if there's a net force. So Fgx prime, and this is the force of static friction. It's not moving to begin with, so the only thing that changes its velocity will be to give it an acceleration. So only if F net is not equal to 0 will it accelerate. That is, change V equals 0 to V not equal to 0. Acceleration. So we have to have a net force, which means that you can see from the picture here that if Fgx prime exceeds the maximum value of the static friction force, it moves. If not, it doesn't. So all I have to do is just say, okay, Fgx prime, does that equal, or you can ask it this way, is it greater than the maximum force of static friction? And all we have to do is put in our equations, that you'll have equations for both of these, the maximum force of static friction and Fgx prime. So we can say mg we said that oddly enough, this time was sine of the angle, is that greater than the force of static friction, which is mu sub k mg cosine of that same angle? Well, we can cancel the m and the g from both sides to make our calculation easier, and we'll pick up with it over here. It really is just asking that question, and I don't know what the answer's gonna be in this one, but we'll be able to get an answer.
We don't have use of K though, we have U.
Oh, I'm sorry, yeah, mu sub s. We've been working with mu sub k all day today. We've been working in the UK all day. Okay, mu sub s, go from the UK to the US. Okay, so sine of, is sine of 40 degrees, that's the question, is it greater than 0.1 cosine of 40 degrees? Probably is, I'm thinking. Okay, and then what do we have for the sine of 40? Does somebody have?
0.64.
Okay, so 0.64, and for the other one, we have,
0.76, and then times it by
oh yeah, okay, so that's definitely, thank you, that's definitely, so we have, yeah, it's true, that, but this is true. In grade school, it said that the big Indian shoots the little Indian, so that's true, that's what they always said in grade school, that's what they said, greater than, less than, how do you remember what that means? If there's a big person with the bow shoots a little person with the bow, that's, I don't know, that,
That's gruesome.
what?
Yeah.
What?
Violent.
Oh, yeah, yeah. What somebody has a hatchet, you know, that's, or like the Harrison Ford thing in the, Indiana Jones, the guy with all the sword play. I don't have time for this, and just bullet, trumps anything pretty much. Okay, so, other questions about this one? This one's just a really straightforward, just knowing that you have to use those equations and seeing, and knowing the condition is that you don't have to go through all this extra analysis over here, you just have to know what you're doing to solve
So
it.
at the end it does move because FGX is greater than FS max.
Oh, yeah, so it does move actually because it overcomes it, and so as long as it overcomes it, so yeah, it does, it moves, so it moves. Yeah, it moves since we can say F net is equal to, you can see from the picture that it's FGX, well, it's FS. Well, actually, the net force, I have it shown in the wrong direction. The net force should be in this direction because it's what's left over. So the net force, yeah, is equal to FG x prime minus F, what is that, FS max. So yeah, so F net greater than 0, that means acceleration is going to be greater than 0 as well, so it changes velocity. So it does move in this case. So you just have to see, are you going to have a net force? If there is a net force, there'll be an acceleration. That means that it'll be a change of velocity in time. And of course, to move, it has to change from 0 velocity to something other than 0. Okay, so questions about this one? This one will probably be on there too. It's a good straightforward question that it'll be quickly, you can show that you know something about the test. You know something about the material right away, even if you get caught up on some of the other ones. On the other ones too, if you can't get started with it, or if you can't get all the way through to the end, do some things that you think might work. Start looking for the equations of what might give me the parameter I need, and I'll give you, of course, partial credit for that. And again, it's going to help knowing exactly what to focus on. Okay. Okay, so that number 7. That's number 7 on my sheet. Number 5 here. Okay, so number 5, I'll give you something like this. We'll have, again, a mass on a flat slope here. Yeah, so we're going to have, we'll be given an applied force. Well, I'll just say here it's 10 newtons. And again, I'll give the mass we'll make the mass the usual 2 grams, and we'll have a use of K value in this case, of 0.3, and we'll say, if its initial velocity at time 0 is 0, what is its velocity after 3 seconds? That's gonna be the question here. What is its velocity after 3 seconds? And there may be a number of ways of solving this, but one of the ways you can say, okay, what do we need? We need a final velocity. Well, we have at least 2 approaches. One, you could say, okay, VF squared is equal to VI squared plus 2AY, but we don't know how far it goes. We don't know the acceleration. We know what the applied force is, but we don't know what the acceleration is because now we're having to take into account the force of kinetic friction that's going to use up part of the applied force. We know what this is, but that we have 2 unknowns with 1 equation. We can't use this one. But let's look at the V of t, which is equal to V0 plus AT. Well, we know this, it's 0. We don't know this, but we know the t is going to be
3 seconds.
3 seconds. So we know that V3 is going to equal to some acceleration times 3. So here we have 2 unknowns we have to find the acceleration and y. Here we just have a to find. So let's find the acceleration, then we can find the answer to our question. And again, a way we can look at this is look at all the forces that are acting in the x direction. To find the acceleration, we have to find the net force in the x direction that I'll just call f sub n without the extra x because we know it's all in the x direction. And so we know that we need net x is mass times the acceleration. We know this way we have an applied force, and we know it's 10 newtons. This way we have F sub k, and what's left over, going in the same direction as the applied force, is the net force. That's what we need to find A. We need this to find A. So we can say, okay, we have, so looking at the diagram, we have F net is equal to FA in its same direction. When we go back, so it's minus F sub k, so we have 10 minus F sub k, that's the net force. So now we need this, but we can get it. We have F sub k is equal to mu sub k, what, mg cosine of the angle. Again, this is 1. Since the angle is flat slope, the angle is 0 degrees. So all we have to get is mu sub k mg, and I get mu sub k as 0.3, using the same mass of 2 and gravity as the fictional 10. We get out of this 6 for F sub k, so now we get the net force is equal to 10 minus 6, or 4. So F net is equal to MA is equal to 4, and that's equal to 2 times A. So that means A is equal to 2 meters per second squared. And so now we have the acceleration. We can go back and get the velocity. So that means that V3 is equal to 2 times 3. So its final velocity is 6 meters per second. And that's another question that may be on the test. Okay. Questions about this question? I have a question that might be or let me give you all a chance, this morning a chance to catch up with this. Okay, so we've got a few minutes still, so that's good. And then after we do these, I can try to answer some of the questions. Well, I'll answer the questions you have about the homeworks for the time we have left. Okay, is anybody still working on, see a few people still, so we'll wait a moment or two here. We've just got, two more to go through here. And that will make a total of 11 that I've given you, and 8 or 9 of those will be on the test, with the possibility of one mystery problem. Or I might replace the mystery problem with, use all 10 of the ones from the ones I gave you, with 2 that I don't use. Okay. Okay, let's go ahead and start looking at our next one. We'll continue on with this flat round with use of K. Then we'll have one final one after that that goes back to finding acceleration in the y direction, normal force, and things like that. Okay, so let's look at this one here. We're going to have an object on, I should have started racing over here first because it's been up here the longest. Okay, so question 6 out of these. Again, we're going to have this object and mass on a flat surface, use of K. And these are so good because they combine so many of the concepts we've been talking about a lot here. So this time we're not going to know the applied force. Okay, what is the applied force? We don't know it. We know M is equal to 2 kilograms. We'll have use of K equal to 0.4. Let's say we know that V at 3 seconds, we know it's equal to 30 meters per second. And we know that its initial velocity is 0. So it's kind of the same one that we looked at, but in reverse. So we're going to find the applied force in this case, using just the clues that we have. So let's focus on how can we find the applied force? Well, what do we know about it? Well, we know that in this direction, we have the applied force. The force of kinetic friction works against it. And what's left over, that's the net force. So in other words, the net force is equal to the applied force in this direction coming back with, so minus F sub K. So again, we have the case that Fn plus F sub K is equal to Fa. And there are other ways that you may could solve this. I'm not saying that there aren't, but this is one good method here, a good approach. Again, the net force is mass times acceleration, which is, in this case, we're using 2 again. We don't yet know our acceleration. So we need acceleration to get this part. So let's look at how we can get acceleration. We don't know the distance that we've gone, so we can't use Vf squared is equal to Vi squared plus 2Ax. We don't know how far we go. But what we do know is a definition of how you find the acceleration when you have a constant velocity. We know that it's the same formula here, and we know that 0 is the initial velocity. We don't know this, so we have as V of t is equal to AT. But we have a specific instance of what this is. We know that V3 is equal to 30, exactly, and so we have A times 3. So finally we get the acceleration is 10 meters per second squared. So now we can go here and finish up getting Fn. So we have Fn is equal to 2 times 10, or 20 newtons. So we have Fa is equal to 20 newtons plus the F sub K. And again, that F sub K is the use of K, mg, cosine of the angle, which again, this is 1.